Good afternoon. My name is Paul Spudis of the Lunar and Planetary Institute in Houston, Texas, and I am this year's recipient of the Columbia Medal. First, I'd like to apologize for not being there in person. I'm currently attending a conference in London, a date that was set quite a while ago, and I really wish I could be there to meet some of you and discuss these ideas with you in person, but in the meantime, hopefully this video will be a good substitute. I'd like to begin by expressing my sincere thanks to the Society for this award. It's very gratifying, and I'm deeply honored to be receiving the medal. I'm looking over the roster of previous recipients, and I see they include my friends Don Pettit, the astronaut, Red Whittaker, the robotics pioneer, and of course Jack Schmitt, the only geologist to have walked on the moon. And all of these guys are friends of mine, and I'm honored to be in their company as the recipient of this medal. I want to speak to you today briefly about the moon and its role in the creation of new spaceflight capabilities. The last 10 years of exploration of the moon have shown us that it contains the material and energy resources needed to create new spacefaring capabilities. And in the next few minutes, I want to convey something of that value that we've found. So, what do I mean by the value of the moon? Well, to begin with, let's look at it from three perspectives. The first value is that it's close, and by close I mean close in spaceflight terms. The average distance of the moon is about 400,000 kilometers, and it is accessible by spacecraft on the order of days to a couple of weeks. This means that effectively you can go to the moon and back in a very short time period, as opposed to the planets, which require many weeks and months of travel time. In addition, it's only 3 light seconds away, a round trip. So that means that we can control machines on the moon directly from control centers on the Earth. It's interesting in that it's a natural laboratory for planetary science, which I'm not going to talk about at length today, but all the processes that work on the Earth and the other terrestrial planets are operative and studyable on the moon. But the most important attribute is that it's useful. It contains the resources of materials and energy we need to create new spaceflight capabilities. Now, why is this? Well, briefly, it's the polar environment of the moon that makes the moon interesting and useful. Because the moon's obliquity is low, and the obliquity is the inclination of the spin axis to the ecliptic. The obliquity of the moon to a perpendicular to the ecliptic. The obliquity of the moon is only 1.5 degrees, which is nearly perpendicular. So that means that over the course of a month, the moon, at the poles, you will see the sun slowly circle your point on the horizon, sometimes slightly above, sometimes slightly below. But that also means that if you're below that local horizon, you'll be in permanent darkness, and if you're above it, you'll be in permanent sunlight. And the effect of that means that you have areas of very cold, permanent darkness near the poles, colder than 100 Kelvin, which is the temperature at which water is stable on the surface of the moon. In addition, you have peaks that might stick up into the sunlight and therefore get permanent illumination. So what you have is a constant source of energy, sunlight, on these peaks of quasi-permanent illumination, proximate to areas located with cold areas that may trap volatile elements. And volatile elements on the moon are extremely valuable because they're relatively rare in the lunar rocks. So to cover the lighting studies to begin with, take a look at these two composite pictures. The one on the left shows the North Pole, the one on the right shows the South Pole. The red arrows point to 2 locations that we've identified that get sunlight for more than 90% of the lunar daytime. They are proximate, you'll notice, to black areas. Black on these images are areas that receive no sunlight whatsoever. In both cases, the crater Whipple at the North Pole and the crater Shackleton at the South Pole, we have evidence that water ice exists in these permanently dark, cold areas. Some of the cold areas near the poles of the moon are actually only 25 to 30 Kelvin, which is an extremely cold temperature. In fact, that's colder than the surface temperature of Pluto, which is about 35 K. But any temperature near the poles lower than 100 K, ice will be stable essentially forever. There's no known process to eject these water molecules out of these permanently dark areas. And over geological time, as the moon's continually bombarded by water-bearing objects, a significant quantity of water ice could build up in these cold traps. So in what form does water occur on the moon? Well, it actually occurs in quite a few different forms. It's derived in part from the lunar interior, we now know. The solar wind implants protons, which can react with metal oxides in the soil and be reduced to hydroxyl and native metal. And finally, water-bearing comets and asteroids constantly bombard the moon and add water to it over time. Now, what we found in spectral data that has mapped the moon from the Chandrayaan mission that India flew in 2009 is that there's a very strong water signal, and that's shown by this figure, the colored figure, which shows blue and purples toward the poles. Above 65 degrees latitude at both poles, there is a water absorption or hydroxyl absorption that increases in strength as you go poleward. So in effect, these are water and hydroxyl molecules that are isolated on the dust grains of these high latitude sites. In addition, when we look at certain craters in the polar areas, we see evidence for relatively bright reflectance. The two maps on the right show the crater, the map on the right shows the crater Shackleton. Remember, the interior of Shackleton is very bright, is very dark. It's permanently dark. It never sees the sunlight. What we're doing here is illuminating the interior with a laser beam carried on the spacecraft, and then we measure the strength of the reflectance that comes back from this laser beam. And what you see is that the interior of Shackleton is very bright, relatively brighter than the surrounding surface. In fact, the two histograms, the black one shows the average reflectance of the surrounding surface. The red histogram shows the reflectance of points inside the crater. So suggesting that there is some kind of bright, high albedo material inside the crater that may be related to water ice. Now, the other experiment we flew was something called the L-Cross, where we crashed a vehicle into the south pole of the moon near the crater Cabeus, and we found that a big plume of volatile material was given off. The strength of that absorption that was observed from that impact plume suggests anywhere from 5 to 10 weight% water in this particular area. And this is an area where we don't see evidence for water in the radar data, which I'll talk a little bit about now. First, I want to talk a little bit about something called circular polarization ratio. When you transmit a polarized wave to the moon and hits the moon and it bounces back, a simple reflection, you get an inversion of the polarization. So you transmit in one sense, say right circular polarized, you should get left circular polarized back. Now there's two instances where you get same sense reflections back. In the first case, you might have a corner reflector formed by a rocky surface. If you have a field full of rocks, you're going to have some that are angled at 45 degrees and others that are angled at 45 degrees in the opposite way, and it forms a corner reflector. So the incident wave is right circular polarized, the first reflection is left, and then it reverts back to right again on the second bounce. So double bounce reflections can give you this enhancement. The other thing that can give you this enhancement is the presence of ice. And the ice has to be fairly thick so that you get multiple wavelength scattering, and you not only get the multiple bounces which enhance the same sense, you also have this effect called CBOE, which is coherent backscatter opposition effect. And that's an interferometric effect that allows waves to actually reinforce each other in the same sense along the axis of zero phase. Now, all the radar data I'm going to show you were obtained from the from the Chandrayaan Indian mission and from the US LRO mission, both of which carried a radar experiment that I was involved in. And they're all monostatic, which means they're all looking at zero phase. So we're going to be seeing areas of high circular polarization ratio. It's not uniquely definitive of ice, but it's highly suggestive of it. So what we find when we look at that data are two kinds of craters. The young fresh craters have high CPR both inside and outside the rims. The anomalous craters have it only inside the rims. Now this is significant because you would expect high CPR inside and outside the rims of a crater that's very fresh. Generates a lot of broken rock, fresh surfaces, you get a lot of that enhancement. If you're seeing high reflections only from the interior, something unusual is going on with that crater. And in the case of the anomalous craters we're talking about, that unusualness is the permanent shadow that we see at the poles. So what we see is when we map these anomalous craters over the entire moon, we find that although they can be found in nonpolar areas, the vast bulk of them, 72 within 10 degrees of the pole, that's only 2% of the lunar surface area, are found on the moon, with the remaining total found all over the entire moon, which is 98% of the area of the planet. In addition, when you look at areas where the shadow is correlated with things like neutron spectroscopy and radar anomalies, we find there's a pretty good coincidence of these anomalous craters. All of these pieces of information suggest that what we have in these craters are deposits of ice that must be on the order of several meters thick. We used S-band radar, that's 13 centimeter wavelength, which means you need about 10 to 20 wavelengths to get volume scattering in COBE. So we're estimating the thickness of these deposits are on the order of 2 to 3 meters. And if you integrate it over the entire zone of the poles, what you're going to find is well over several hundred million to 1 billion cubic meters of water ice. Now, I've gone on a bit about water, and the reason I had done that is because water is probably the single most valuable substance you can have in space. Obviously, it's a source of life support consumables. You can drink it, you can use it to reconstitute your food, you can use it for sanitation, but you can also break it into its component hydrogen and oxygen and breathe the oxygen. So it provides air and water for long-term human presence in space. In addition, the gases, hydrogen and oxygen, can be combined to generate electricity. And when you have electricity generated from another source, like a solar array, you can crack water into its component gases. So in that sense, it's a medium of energy storage. When the sun is out, you crack water into its component gases and save them. When the sun is in eclipse, you combine them in a fuel cell to generate electricity. It's a completely reversible process. Water is some of the best radiation shielding we know of. So jacketing a habitat on the moon in water allows us to protect the crew from harmful cosmic rays and solar particle events. And finally, the most important use of it all is to use the hydrogen and oxygen from water, cryogenically freeze it into a liquid, and use it as rocket propellant. Liquid hydrogen and liquid oxygen is the most powerful chemical rocket propellant known. And if you were able to create rocket propellant from lunar materials, you're able to refuel your vehicles and refuel your vehicles on the moon and in space, cislunar space, the area of space between Earth and the moon. Learning how to do this is a fundamental requirement of long-term human presence in space. We need to be able to take what we find in space and convert it into forms that we can use to support whatever activities we want to do. So one of the things I've been looking at in the last few years is developing the moon and cislunar space primarily through the exploitation of lunar water and using some of the findings we found in the last few years. So our goals are to extend human reach beyond low Earth orbit by building a permanent spacefaring infrastructure. So we're talking about space-based assets that are continuously reused and refueled on orbit and on the moon. We want to learn how to use these material and energy resources because that information, skill, and technology is applicable any place in the solar system. Any place we go, we're going to want to learn to use local resources. It makes sense to start at the moon, where we have two of the most valuable resources present in forms that we can already use and readily use. We want to develop a plan to return to the moon in small incremental steps. You don't want to have to come up with a plan to put down a multi-billion, $100 billion base on the moon. You can actually approach this incrementally with small robotic assets that are remotely operated from the Earth. So in fact, this is a way to go back to the moon that doesn't break the national bank, and at the same time in places permanent infrastructure and assets that can be used to create long-term capability. We've also assumed in this that schedule is the free variable. We don't really care how long it takes as long as we continually move toward an endpoint that's defined as having a permanent space transportation system. Now, the way you do this is in a set of incremental steps. All of these missions that I'm describing here are all robotic. They can all be launched on existing expendables, launch vehicles, or they can be combined together in some future heavy lift vehicle. The first thing you're going to need is a set of communication satellites because the poles are sometimes out of Earth communication. So you need to have relay satellites that give you constant comm wherever you are around the poles. Now, we don't know enough to put down a resource processing base right now. We sort of know where the highly lit areas are near the poles. We don't know where the best ice deposits are. So we need polar prospecting surface elements. And I've proposed both hard landers, soft landers, and rovers to get the necessary information. You need to prospect this just like you were prospecting a mining site for mining recovery on the Earth. The first thing you do after you have that data is to land a small spacecraft that will demo the process. And the demo here consists of digging up ice-bearing soil, heating it to a certain amount so that the water gets vaporized, collecting that vapor, and storing it in some kind of storage tank. And once that's done, you've actually demonstrated the entire amount of processing you're going to do on the moon. In addition to water, there are other volatile elements of use on the moon. There's methane, ammonia, and some simple organics, as well as carbon dioxide and sulfur dioxide. All of these come from cometary sources, probably, and therefore we can, when we collect the water, we can store the byproducts for use, future use of industrial processing on the moon. So to get at this feedstock, this icy regolith, you need to dig it up and haul it back to some central processing location. There may be better ways to do that, by the way. We may be able to find out a way to extract this stuff without moving dirt, but as of right now, this is the only way we know how to do that. Then you want to process it by heating it and store the processed water in tanks. If you're going to use it as rocket fuel, you need to crack that water into its component gases. And there's a two-step process. First, you electrolyze it by passing an electrical current through the water, which makes the two gases, hydrogen and oxygen. Then you freeze those gases into their liquid form. Now, hydrogen is very, very cold. Liquid hydrogen is very cold. It's 20 Kelvin. But since the cold traps near the poles are on the order of 25 to 35 Kelvin themselves, it's not going to be very difficult to keep that stuff nice and liquid. There's a variety of supporting equipment. We've got two kinds of robotic landers. Power plants are simply robotic landers with big erectable solar arrays that deploy themselves like window shades and then turn about their vertical axis so they can track the sun as it moves around the horizon. And a variety of 3D printing material fabricators to help build the infrastructure of the outpost. We have two depots for to store the product and for the spacecraft, one in low lunar orbit and one in low Earth orbit. So in effect, what we've done here is to use these robotic assets, these small pieces, as a cumulative system of systems to create a system that will go from the raw lunar materials of the poles, the manufacture of water and the storage of that product, and the making of rocket propellant. Now, once you've done that, people can come back to the moon. This way, we effectively emplace the lunar outpost and all the associated infrastructure robotically via teleoperations so that when people come to the moon, they move into a working turnkey operation. It's incremental, so it doesn't matter what the budget is in any given year, because if in a fat year you get an extra budget, you make more progress, and in lean times you scale back and you go slower, but you never go backward. You always go forward. You're always moving toward an endpoint. In effect, what you're doing is you're setting up a system that will support itself and create a long-term cislunar transportation infrastructure. So our goal is permanent presence on the cislunar frontier, using the resources of the moon to create an affordable and extensible space transportation system. And I think this is enabled by the presence of the energy and material resources of the moon. By doing this, you learn skills that you'll need no matter what your ultimate destination in space is. This system can not only access the moon, it can access all the points in between Earth and Moon, cislunar space, and that's the zone of space where all of our satellite assets reside. So you're gradually going to move away from a paradigm where you're launching unique assets that get thrown away after use to one that's where you build long-duration systems that are extensible, maintainable, and upgradable over time. So I think that the moon is an enabling asset. In fact, it's a gateway to the universe, because the things we're going to do on the moon are going to help us colonize and move out into the solar system. It's the ideal place to learn these skills, and that's what I work on, and I appreciate your attention. Thank you very much.